Hi, everybody. We're starting section 3.1, and this is the definite integral. And basically, we have a curve, y equals f of x. It's on the xy, coordinate system. And I'm looking at the area under the curve. The area under the curve. That's this area right here. And by the way, when I say under the curve, I mean between the curve and the x-axis. Because if I would say under the curve, that could go down infinitely forever. I'm just talking between the curve and the x-axis. Um, so I'm gonna write uh, under curve means between curve and x-axis. Anyway, this area that's under the curve turns out it's actually very useful to know it. And finding area, that's something we always did in geometry, but this I don't know I know a formula for a triangle, I know the formula for the area of a rectangle. I don't know a formula for the area of some random, curve. Um, and that's the problem. And that's actually what I love about that's one of the things I love about calculus. The calculus is very I'm gonna say plucky, meaning to say don't have a formula for the area of a random curve, no problem. We'll figure one out. We'll find the area without a formula. We'll do it. We'll figure it out. That's what I love about calculus. Very kind of cool. Before I do that, I want to just give you a notation. This area under the curve, area under a curve, in this case between point A and point B, um, the area is equal to the way we write it. We write it this big symbol, big. It's like a giant stretched out S. And the fact that it looks like an S is not a coincidence, because think of S for sum, SUM. Anyway, we're looking at the integral. We call it an integral sign, by the way, from A to B. So we're going from point A to point B of this curve, f of x, whatever it is. And we always add this symbol here, dx. And we're familiar with the dx. We've seen it with derivatives, and this is the area. This is called a definite integral. This is a definite integral. Definite integral. And what makes it definite is the fact that you have an a down here and a b down there. So, for example, if I wanted to have the area, let's say I have a parabola here. Let's look at a parabola here. Y equals negative x squared plus 5. I'm going to graph it. And it starts, it starts up here at 5, and it goes all the way down. It goes down forever. But I want to look at the area under the curve. Now, by the way, what is this point over here? This point here would be rad 5. Because look here, if x is equal to rad 5, I would have negative 5 plus 5, and that would be 0, which is supposed to be. So I want to find the area from x equals 0. Let's say x equals 2. I want to find this shaded area here. Notice I'm not. Notice that I'm not going. I'm not entering this little white zone right there, that little blank zone, a little blank space, if you will. I like to call it a blank space because I'm a big Taylor Swift fan. And there you go. So we want to find this area, the shaded area under the curve. This is the curve y equals negative x squared plus 5 between the curve and the x-axis between the values of x equals 0 and 2. So the way you'd write this is the integral from 0 to 2 of negative x squared plus 5, because that's what the function is, and then you write dx. So this means the area under the curve negative x squared plus 5 between x equals 0 and x equals 2. And when I say under, I mean between the curve and the x-axis, because under could go all the way down forever. But we're not talking about going all the way down forever. We're talking about just this much. Okay. So let's see how we'd attack this. I'm going to draw. So what I love about calculus is that it's very plucky. You know, I never learned the formula for parabolas in geometry class, even though there actually is one. But you know, let's go and let me see what I'm trying to say. If we look over here, I'm going to draw this on paper, but I want to show you in a more professional drawing, so it's a little more clear. Here's the curve y equals negative x squared plus 5. I'm going to draw 1, 2, 3, 4, 5 rectangles, and I'm going to draw a dotted line in the center of each rectangle to the point where it hits the curve. So there's the pow, 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 pow. Okay, so let's and the place where this dotted line hits the curve, that's where I'm going to draw the top of the rectangle. Well, I think it's easy to show you on paper. I want you to see this diagram here, because when I draw it on paper, just in case it's not as super neat as it could be, because I'm not an artist, so I want you to see what it's supposed to look like. Let's go back and here you see what it's supposed to look like. This is the diagram I'm going to draw. But I'm going to draw it again. I'm going to explain each point. Okay, so let's get started. Let me switch cameras again. Let me stop the share and switch cameras. All right. So I'm going to draw this. So first of all, we're going up to 2, from 0 to 2, making 5 cuts. So each cut will be 2/5. That's right. That's 2/5 right there. That's 4/5. That's 6/5. That's 8/5. And that's 2, which is 10/5. Now, what I'm going to do is I'm going to take the midpoint. So I have 5 segments here, from 0 to 2.5. Then I have an interval from 2.5 to 4. Then from 4, not 2.5, 2/5 to 4/5, and 4. Then I have an interval from 4/5 to 8/5. Another interval from 8/5 to 6/5 to 8/5, and then from 8/5 to 8/5 to 10/5. Boy, I can't talk anymore. That's what it is. So what I'm going to do now, I'm not going to draw lines from here up to the top. What I'm going to do is I'm going to take the midpoint. It's called midpoint. Midpoint is very important here. I'm going to take the midpoint of each interval. So here's my first interval, and that's the midpoint right there. Here's my second interval, and that's the midpoint right there. And again, these intervals should be evenly spaced. I didn't draw it perfectly evenly spaced, like I said. I have my limitations. That's the midpoint of the third interval. Here's the fourth interval. That's the midpoint of the fourth interval. And here's the fifth interval. That's the midpoint of the fifth. And this part over here doesn't count. We're only going up to the 2. We're not going beyond the 2. Now what I'm going to do is I'm going to draw a dotted line from the midpoint until it touches the curve. So this point is going to go and touch the curve. Now, what is the x value of this midpoint? Well, if this is 0 and that's 2/5, this is 1/5. That's the midpoint. And what is now I'm going to go to the next midpoint of my next interval. We're going to draw a line. I'm in the midpoint now of my second interval. And that midpoint, of course, is 3/5, because it comes right between 2/5 and 4/5. Then I go to my third interval. Well, the midpoint there, which of course is 5/5, which is of course equal to 1. I'm going to draw that line. And now the next dotted line. Of course, that's 7/5. And the last dotted line, 9/5. Now, this is now going to be, so what I'm going to do now is that I'm going to draw a vertical line through each of these little points. Draw a vertical line. I'll finish the vertical line in a second. We'll draw a vertical line right through right where these dotted lines intersect the curve. And this is going to be the top of my rectangle. So I'm going to draw this line here. So it hits that right there. And I'm going to draw it. Now this is going to hit the side right there. And here I'm going to extend this guy. Okay, so I have rectangle 1, rectangle 2, rectangle 3, rectangle 4, and rectangle 5. So I have now 5 rectangles. And the height, what's the height? Well, remember, the curve is y equals negative x squared plus 5. So the height of this first rectangle is going to be negative 1/5 squared plus 5, which is equal to 5 minus 1/25, which is, oh boy, 4. And I'm going to want to use a calculator for this. That's well, that's 5 minus 1/25, which is 4 and 24/25. So what is that? Let's not write it that way. It's going to be, let me write that. Let me figure this out as a decimal. It's going to be 4. Minus 1. It's 4.96. The height here is going to be 4.96. That's the height, meaning that's the y value of that point. The x value is 1/5. Y value is 4.96. I'm realizing now that decimals is going to be to our advantage. Either way, the next one, this is it's negative. We're going to write these as decimals. 3/5 is really 3/5 is equal to 0.6. So negative 0.6 squared plus 5. That's the second height. The third one is going to be negative 0.1. Negative, I'm sorry, 1.0 squared plus 5. That's easy. That's just 4, because it's just 5 minus 1. But let me get this one here. That's 4 right there. And let me just let's see, negative 6 squared. That's 4.64. And here we have 7/5 is 1.4. So negative 1.4 squared plus 5, that equals, that equal, uh, 3.04. And finally, we have 9/5, which is 1.8, negative 1.8. Let me just figure that out on my trusty calculator. That's 1.76. Well, so so if I would add up, and this is the beauty of calculus here. I don't know a formula for the parabola, but if I add up these 5 rectangles, it's going to come. Don't forget this part here doesn't count. Not that doesn't count. I just drew it in, but it doesn't count. It's not part of our. It's not part of what we're looking at. We're just looking between 0 and 2. So if I add up these 1, 2, 3, 4, these 5 rectangles, it gives me, brings me pretty close to the area under the curve. Not 100%, but it's pretty darn close. I mean, if you think about it, it's going to overestimate over here, but it'll underestimate there. So that kind of balances out a little bit. It goes over here, but it goes under there. So again, it kind of balances out a little bit. Over, under, over, under, over, under. It's not perfect, but probably come out fairly close. So we'll check that out in a second. But what is the width? What's the width of each rectangle? Well, each rectangle is the same width. Each rectangle has a width of 2/5. All I got to do is add up these 4 numbers: 1, 2, 3, 4, 5. Add up these 5 numbers, and multiply them all by 2/5. So it's just going to be, so the area, the approximate area is going to be 2/5, which is the width of the rectangle, so that's 0.4, times 4.96 plus 4.64 plus 4 plus 3.04 plus 1.76. And let's crunch that out right now. I'm gonna put that in my handy dandy calculator. 6 and 4.96 plus 4.64 4 plus 3.04 plus 1.76. No, I want to multiply that times times 7.36. That gives me 7.36. So the area under, now, of course, is it perfect? No, but it's a decent approximation. It's a decent approximation. At least it's something. It's better than it's better than nothing. Better than having nothing. I will tell you though, spoiler alert, the actual area, the true area under this curve, if you would do it, fully precisely, is actually, I'm going to use different colors. The actual area is 7.333. And this is, look, 7.36. So we came fairly, I mean, that ain't bad. That is not bad at all think considering we had nothing before we started, and now we got this. So this is we're going to formalize this. So I'm going to stop this video now, and then next video I'm going to formalize this process a little bit more. But this is pretty darn good. So so I'm ending it now, and I will see you guys next time. Bye.